So now let's talk about the implications of holding inventory in multiple locations versus a single location. And we're going to do this through an example. This is the Med-X case, and it's based off of a thesis that was done up here at MIT in 2005. So Med-X is a medical device manufacturer, and they deliver products directly to hospital wards, a pretty common practice these days. One item, the X104, is used by 3 different wards within a certain hospital, the Northwest Hospital, and the daily demand at each of the wards is normally distributed with a demand of 22 with a standard deviation of 4.6. The cost is $156 each. Lead time is 2 days. Transaction order cost is $40. Holding charge is 20%. Cycle service level is 99%. And we're going to assume a 365-day year here for this analysis. So currently, each ward manages their inventory independently, and they work with Med-X directly, and they each use an SQ inventory replenishment policy. So the question we want to figure out is how much cycle and safety stock should each ward hold? This should be very easy. You guys should be experts at this by now. So what do we want to do? Well, first we want to find the average cycle stock. So I want to find the Q star. Q star is simply going to be equal to square root of 2 times the transaction cost times the annual demand, 365 times 22, divided by the cost of excess, which is just the purchase cost times the holding charge. And that gives me 143.5 units. I'm rounding it up to 144. So your numbers, if you do this at home, might be slightly different from mine due to the rounding you make and the number of significant digits. So I will always tell you where I cut off for the significant digits, just to make sure that your numbers come out close to what mine do. So then, to get the average cycle stock, we just divide that by 2, right? Q over 2 gives me 72 units. Now we want to find the safety stock. Well, I know my expected demand is 22 per day. My lead time is 2 days. So expected demand over lead time is 2 times 22, or 44 units. My standard deviation of demand over lead time, I had a 4.6 times square root of 2, 2 days again, and that gives me 6.5 units. I was given a cycle service level of 99.9%. I can look on a table or use a spreadsheet and get a K of 3.09. Therefore, my average safety stock for each of the wards is going to be 3.09 times 6.5, or 20.1 units. And then across all 3 wards, since they're each managing them separately, right? You can think of these as each separate ward is doing by themselves. So I sum them all up, and I get that their cycle stock will be about 216 units, and their average safety stock is about 60 units, 60.3. Okay, but what happens if they pool their inventories? Instead of keeping them at each of these different locations, they put them center. Let's say they put them all right here in one location instead of keeping 3 separate little inventory piles. What will happen? Well, what do we need to do? First thing we need to do is figure out what is the pooled demand, or that common demand for all 3 of the wards collectively. Well, if we know that each ward has a demand of 22 with a standard deviation of 4.6, then 3 of those added together, the expected demand each day is going to simply be 3 times that, so 66 units. To figure out the standard deviation, remember that if I have the variance of a sum is just the sum of the different variances, or I can simply say that the standard deviation of the pooled demand is equal to the standard deviation of each of the wards times square root of n. So it's the same thing. I could likewise turn this into a variance, square it, and multiply that by 3, then take the square root of it, but it's the same thing. So we end up with 4.6 times the square root of 3 gives me 7.967. I'm going to use a value of 8 there. All right. So now we want to find the average cycle stock. I do my Q again, and what's changed? 2 times the transaction cost hasn't changed. The total demand has changed, right? 365 times 66 a day, and the C sub E has not changed, but I end up with 248.5. I'm just going to use 250 units going forward. So a Q of 250, cycle stock is half of that, 125. Then my safety stock, I know my expected demand for each day. Then over lead time of 2 days, I get 132 units. Same thing for the standard deviation, taking the the standard deviation of demand on a daily basis times square root of 2 gives me 11.3. I've already figured out my K previously, so my average safety stock is simply going to be K times that sigma DL, which gives me 35 units. So across all three wards, right, I'm going to have a cycle stock of 125 units and a safety stock of about 35 units. So let's compare these two strategies. So here's my simple table, and I've got 4 columns. The strategy, whether it's independent, each ward is doing it separately, or it's pooled and they're doing it collectively. My average cycle stock in units, my average safety stock again in units, and the average total inventory, just the sum of them. Now I could have just multiplied each of these by C sub E, the cost of having excess or having inventory on hand, and it'll give me dollar amounts, but it's just a straight multiplication. So what do we observe? Going from each ward independently managing down to where it's being pooled. In each case, the amount of inventory goes down. How much does it go down? By the square root of 3. You can verify that really quickly if you want. But why does that happen? Is it just coincidence that they all just happen to go down? And the answer obviously is no. So let's look and see what happened. So let's break it up and look at both the independent, where each ward is managing separately. So I've got 3 wards here, Ward 1, Ward 2, Ward 3. And then here's where it's collectively as a whole, where it's pooled. And so for each of the individual wards, I've got a separate little queue here. And so I've got, each one has their separate little cycle stock, and then they've got their safety stock that it's floating upon. And so the question is, why does the sum of, say, all these safety stocks, why is it not 1/3 of this? Why isn't this safety stock equal to the sum of those? The same thing with the cycle stock, here. And then what I've got here for this is for cycle stock and safety stock. So let's look through. Let's look at the pooled situation for cycle stock. How did I figure that out? Well, this is the easiest one, right? I looked at the annual demand, right, and I figured out just a Q star for everything. And so the average inventory on hand is just Q star over 2. So that's pretty straightforward once I knew what the annual demand was for the pooled set of all 3 wards. How did I do it for when it was managed independently? Well, I looked at each individual ward, and I used a small q there, and I used the same equation, but what did I use for the D sub I? The annual demand is the demand that one ward gets, not for the whole thing. But I know that D sub I is simply equal to the total demand divided by the number of wards, D over 3, right? It's getting 1/3. They're all the same. So if I carry that through, what that dictates is that the inventory on hand is square root of n times that Q star of the whole pooled amount, all 3 wards, divided by 2. So that's where my square root of n comes in cycle stock. Where is that happening? What's causing that? Well, if you think about it, the thing that's really changing, that's not changing here really, is the C sub t. So because the C sub t is not changing, so if I get a delivery to a ward, it's going to cost me just as much per order as if I have a separate delivery for the pool as itself. So the individual ward deliveries cost the same amount on a per order basis as a delivery to the pooled amount. Because that's held constant, that's where that square root of n comes down. Okay, now let's go to safety stock. Again, for the pooled area, it's simply going to be that safety factor K times the expected demand over lead time for all of the pooled inventory, all 3 wards collectively. Well, here for the individuals, it's going to be for each ward this amount, sum that up for each of the 3, and so that's actually what you're doing is you're taking the standard deviation and you're breaking it down into the individual ones. So we can see that would simply be the square root of n times that total demand. Again, because it's like summing the variances, and then I take the square root of that to get the standard deviation. Same thing here. So the reason why this goes down so much for safety stock is something that's known as risk pooling. Let me just write that down. So the whole idea is the idea of risk pooling, and this is very commonly used, and we'll talk about it again in a few minutes, but it's also sometimes called the square root of n rule, right? where if I go from an inventory of 3 units here down to 1, then I will reduce my inventory by square root of 3. Well, that's a horrible 3. Let me write that again. There we go. That's a little better. Anyway, we'll talk more about this, but what I want you to make sure you understand is if I go from many inventory locations, 3 in this case, to just 1, my inventories will go down, both cycle stock and safety stock. And they'll go down for different reasons. Safety stock, you're balancing out the demand, so it's risk pooling. Cycle stock, it's because the transaction or order cost doesn't change.